Alright, let's get this party started. So, the reason why I'm even on camera to begin with is we are, I would say, in the middle or recovering from the COVID-19 pandemic in the year 2020. These videos will definitely be posted to my YouTube page indefinitely, so figured I'd document some history along the way. They're going to be primarily intended for my UF students at Rutgers University, so if you are some stranger watching these videos, I'm talking predominantly to those students that I'm teaching right now. But I suppose we shall get the party started. So we begin our foray into calculus with this idea of a limit. So why is a limit that much of a big deal in calculus? It establishes the foundation for what we typically enjoy doing in calculus, which would be differentiation and integration. And now, why the need for a limit? It just seems like, okay, we take this value and we substitute it in and we move on and everyone has a happy day. But limits were conceptualized centuries ago because what happens when we have values of a function when x is approaching a particular number c, when f of c is or is not defined, the key piece being here is not. Okay. Let's take a function, for example, f of x equals sine of x over x. Nice and rudimentary for the most part. Just kidding. I know for many of you sitting at home watching this, you see a sine function and your palms are already sweating and your armpits are sweating and the anxiety is bubbling. Fear not, we will get there. But let's evaluate this at f of 0. So if we substitute that into the function, we arrive at sine of 0 divided by 0. If you're unsure at this point of your pre-cal, I'll probably put together some pre-cal magic tricks. But sine of 0 is indeed 0, and 0 over 0 leads us to what we call in calculus the indeterminate form. So now what? Now what do we do? How do we know what this function is doing if it's undefined at that particular value? Well, enter said limit. So we're focusing first and foremost on a numerical approach, and then we'll look at this graphically. So if we had a table of values, right? So we said we looked at f of 0 sine of x over x. We got 0 over 0. So let's say we wanted to look at the values as x approaches 0 from the right. So we want to indicate that we do a miniature plus sign on the right side of the numerical value. This means from the right. So let's take values like 1. Okay, and f of x, what we find out is 0.8414709. But 1 is still far away, so let's get a little closer, 0.05, and we jump to 0.99583, 0.005, and you should notice a trend starting to establish itself, and 0.001 being 0.9999, so on and so forth. So we use a different color here. We can say approximately 1. Now, what does that look like from the opposite side? So if you're fresh to calculus, right, remember this is from the right side. So this would be from the left. We would use a miniature negative sign on the right hand side of the number. Okay, so just flipping these values around, if you know anything about your trig functions, and if you don't, no sweat off your back, I don't even know who you are, you'll come to see that trig functions are circular, aka they are symmetrical, so these values coincide. So we can say that from the left and the right side, even though the function has an indeterminate form at f of 0, as we get closer and closer to this idea of f of 0, from both the right and left hand side of the function, it's tending towards 1. So we know that the behavior of the function as it approaches 0 is 1. It's just not defined concretely at that value. If I were to draw a graph, now I hope I have enough room to draw you a graph. Set our axes -3 pi, -2 pi, negative pi, pi, 2 pi, 3 pi, and let's say that this value is 1. So once again, we know that this value is undefined, so let's put a hole here, okay, at f of 0, and our function is behaving something similar to this. So symmetrical, as far as my Vincent van Gogh skills go. But we can see that both from the right and the left, as we're approaching x equals 0, the behavior of the function is to tend towards 1, even though it is not defined at that value. So what we say is the limit as x approaches 0 of f of x is equivalent to 1. Right? Because it's this idea of trying to understand the behavior of functions that algebra has a ceiling towards, right? Algebra restricts us. Okay? Without the use of graphing technology, this tells us nothing aside from the fact that it's undefined at that value. But if we want to understand what the behavior of that particular function is and how it could apply in our everyday phenomena, we need to rely on this idea of limits. So, what's our key takeaway point? After our first look at limits in the world of calculus, is that a function f of x may approach a limit as x approaches c, c being some arbitrary number, even if the formula for f of c produces an undefined expression 0, 0 being the example that we just worked with. So let's write down our first definition. That being a limit. Assume that f of x is defined. You'll start seeing me use some symbols. So if we have an upside down A, this stands for all. Alright, so assume that f of x is defined for all x in the open interval containing C. But not necessarily at C itself. Just like our beginning example, we say that the limit of f of x as x approaches C is equal to L. Or no space to L if, this is the key piece, the absolute value of the function minus the limit becomes arbitrarily small when x is any space, x is any number sufficiently close but not equal to C. We can then write the limit as x approaches C of f of x equals L if the values of f of x do not converge to any limit as x approaches C. We say the limit does not exist. All right? So picking up where we left off on that definition of a limit, let's verify this limit, okay? Now, you might be watching this video with some prior calculus knowledge, so you're like, yeah, Joe, of course. 6 plus 4, substitute there, 3 times 4 is 12, plus 1 equals 13. But slow down, speed racer, we want to make sure that we have a very solid, foundational, conceptual framework of limits in order to be more successful later on down the road when we start to get to the definition of a derivative and this idea of the fundamental theorem of calculus. So, let f of x be equal to 3x plus 1. Okay. Then according to the definition, we need the function minus the limit to get arbitrarily small. So, we take the function 3x plus 1 minus the limit value, which is 13. We algebraically simplify, and we arrive at 3x minus 12, which we can further simplify to this expression. 3 times the absolute value quantity of x minus 4. So since f of x minus L is a multiple of 3, oops, that should not be in parentheses, 3 absolute value quantity of x minus 4, we can make x minus 13 arbitrarily small by selecting values of x sufficiently close to 4, right? Because if I selected a value sufficiently close to 4, let's say 4.001, okay, and I substituted in here, well, 4.001 minus 4 is going to yield me 0.001, which I would then multiply by 3, and would yield me 0.003. Thus satisfying this definition of a limit by allowing it to become extremely tiny. And as we get closer and closer to 4, right, we could take 4.0001. And on the flip side, we could take 3.999, 3.99999, etc., etc. Since we have an absolute value bracket here, we'll turn that positive, and by doing that multiplication, this value is only going to increasingly become tinier and tinier. So the upside is graphical and numerical investigations provide us some insight. So here we satisfy the definition of a limit, but previously, in the previous example, we had done it graphically and numerically, but that does not prove that a limit exists. We must do that using limit laws. So let's take a look at another example. Function a little bit more straightforward. Okay. And yes, once we take off the training wheels and the kid gloves, we'll be able to get, past the very tedious and very arduous, painstaking process we're taking right now. But we do want to ensure that we have a very solid framework. So once again, let's take a look at this function as it approaches 4 from the right. And let's take a look at this function as it approaches 4 from the left. So we got 4.1, 4.01, 4.001, 3.9, 3.99. And, since you're looking at a calculus video, you should be aware of the shape and overall behavior of that function. But if you're not, I'll draw a picture in a second. But we can see here that if I probably took 4.001, this would just become 16.008, whatever the case may be. So we can assume that this is trending towards 16, and quite similarly on the opposite side of 4, the behavior holds true. Alright, so we have x squared, 16, 4. There. So why this example as compared to the previous one? Two things. In the original example, the value of sine of x divided by x at 0 was undefined. Here, the value of f of 4 is indeed 16, which is also the limit. Okay. Now this only holds true in one scenario. The limit is equal to the function value only when the function is continuous. Okay. The function isn't continuous, well, then this auto substitution that you'll come to learn about is useless. Hence, the numerical and graphical investigation of limits. That's where we're going to take a 30-second pause and we'll pick up our next video with one-sided limits.